Hi everyone, I'm Hakala, and my today's topic is generative adversarial networks. I was requested to keep this as non-technical as possible, so I don't have a single formula or not even picture of neural network in this presentation. I hope you guys like it. My own background is in language technology, so that's why there is also this for text mention in the title. All my hands-on experience with generative adversarial networks is based on text, and there will be like slight bias or emphasis on text generation in this presentation. Here's the overall outline, what I was planning to talk about. So first, I will give you like really quick bio, what I've been doing and who I am, and then we have this funny little OCR project that I want to talk about, basically because this is the project that led us into experimenting with the generative adversarial networks, or GANs in short. So hopefully it will work as some sort of motivational background story. Then we will get into the actual topic, how these things actually work and what they are. And then I will also talk about some issues that people usually face in practice when playing with these tools. And finally, I will try to give you some sort of summary that what is the current state of the research in this field. So, who am I? I'm a PhD candidate at the University of Turku at the moment. I work in the Turku NLP group, which is a language technology research group at the university. I've been doing NLP, or natural language processing, since 2011, so roughly 7 years now. And mostly I focus on text mining in the biomedical and clinical domains. So all sorts of information extraction and text classification with patient records and that kind of stuff. That's pretty much all I have to say about myself. Yeah, so let's get started. The project that we've been working on is related to OCR. So the Finnish National Library has this funny little news archive where they have digitized pretty much all Finnish newspapers they have access to, starting from the 18th century. So they have scanned all the newspapers and then ran an OCR system to convert them into text. And this is pretty much what they then in practice have. They have something like 13 million pages that looks like this stuff on the left, and then they have the OCR text version of the same stuff, and the quality is not that great. So the goal in this project is to fix that text into something that actually makes sense. So if we take some sort of input sentence that has a couple of broken words, we would like to somehow process this into like actual Finnish clean text. That's the goal of the project. This is actually pretty standard type of problem in language technology. So the input is a sequence of text, and the output is also some sort of sequence of text. And we can pretty much use the same machinery that is used in neural machine translation, and these models are called sequence-to-sequence models in general. In our case, it's a character level model, so it's reading the input one character at a time and then producing the output one character at a time. And if we think this problem as a machine translation task, we can basically say that the source language is now the noisy text, and the target language that we are translating into is the clean text. Those of you who work with autoencoders can also think this as a denoising autoencoder model. That's basically what it is. This model works pretty well, at least to some extent. So we are able to fix almost half of the errors in the current OCR system that they are using at the National Library of Finland. The problem with this is that we actually need some sort of gold standard training data to get into this type of results. So that's the catch here. The training data has to be paired in a way that we have the same text, including the OCR noise, and then manually corrected version, basically. Luckily, the National Library of Finland has this type of data, so that's why we know that we can actually correct the data to some extent with these sequence-to-sequence models. But in general, the case is that we don't have this type of training data at all. So we started looking into ways that how to generate synthetic training data instead of using manually corrected one. Yep, there's a question.
Yeah, so you have a basically 50% decrease in error rate.
Yeah, on word level.
Manually corrected data. How much of data do you need to?
So the amount of data we used in the manual with the gold standard data is on the level of like 300,000 tokens worth of manually corrected data. So it's already pretty cumbersome to actually come up with that type of data set. Yeah, so the idea, we would like to generate synthetic data basically by modeling the errors that the OCR system is doing, and then introducing that type of noise into clean text. So this way we know what the clean text has been, and we have the noisified version of the same data. One of the ways that we started doing this is that we noticed that there are actually plenty of repeating text in the whole dataset. So same news get repeated in different newspapers, and the has been the same, but there are some differences since the OCR in data should be as close to the target text as possible. And since this is like old Finnish newspapers using like modern Finnish as the clean underlying text doesn't really work. It's quite different type of language. So the closest we can get is this Kotus early modern Finnish corpus, which is roughly from the same time period as the newspapers, but it's mostly fine literature and not real news data. But that'll have to do. So this thing actually works quite well. Not even close to how far we can get with the manually curated gold standard training data, but we can still fix some of the errors that are present in the OCR text. So we had a nail and we built some sort of hammer for it. The problem is that the hammer is kind of small, and that's not really a nail, it's a pin or something else. But anyway, so we started thinking that, okay, what would be like a fancy, really hip version of solving this problem? And that's where the GANs enter the picture. So what these things are. Generative adversarial networks are a type of neural network training mechanism, basically, or some sort of like machinery. And these are usually used for generating some sort of realistic samples. If you are talking about pictures, then usually we are talking about photorealistic pictures. If you're talking about text, then hopefully it will produce some sort of fluent text that looks like some human has written. The nice thing about these is that they are basically unsupervised. They don't need any sort of manually curated data sets to be able to produce these type of samples. At the moment, these are extremely hyped. The research field has been growing exponentially during the past years. And the basic idea behind these networks is that we have actually two different neural network models that are competing against each other, and they are trained jointly. I will go through the basic idea shortly. These really poor quality faces are generated by the first generative adversarial network ever. Well, not probably the first, but they are from the first GAN paper ever published, and that was in 2014. So this is still like pretty decent technique in machine learning. So how do these things do with text? Here is a quote. I've tried many different brands of hot sauces, but this one is the best. I've also used it in soups and stews. I also like that it is organic and has a great flavor. And this text or review was actually produced by a generative adversarial network from a paper, very recent paper from this year. So this is pretty much the state of the art in producing text with this type of models. So, how do these things actually work? I mentioned that there are two different components in this model. The first part is the generative part of the model. So here, the generator, and there was some sort of analogy with electricity and AI in the previous presentation, so maybe this somehow fits in the same theme. So the idea of the generator is to produce the actual samples that we are interested in. So let's say that we are interested in pictures of dogs, then we hope that our generator will be able to produce different type of pictures of dogs. But since this is a normal neural network, the generator, it doesn't actually have anything fancy inside. It's completely deterministic. So how does it actually produce different type of outputs? Well, the answer is that we also have to introduce some sort of variation in the input. So in practice, these models usually take some sort of seeds as the input, and these can be for instance, completely randomized vectors. So that's basically what the generator part in the model does. Then we have the adversarial part in the network. So the second part is usually called the discriminator. The whole purpose of this part in the model is to detect whether a given some sort of sample, in this case a picture of a dog, is real or fake. So that's what the discriminator tries to do. So we have a model that is building these, creating these or generating these pictures, and we have a model that is trying to figure out whether they are real or fake. That's what these components are doing. And the real magic actually happens in the training. That's the most important part in the whole system. So the way we do the training is that we first sample some entities, pictures of dogs for instance, from our generator, and then we need to have some examples of real entities. So we then sample, in this case, pictures of dogs, like real dogs. And once we have these samples, we can train the discriminator to distinguish between these. So the discriminator is trained in basically the same way as any supervised classifier, basically a binary classifier. So we are telling that this set is generated ones and the other set is real ones, and we hope that the discriminator learns to distinguish between them. Then the important part is how the generator is actually trained. So we are never telling the generator that what a picture of a dog should look like. Instead, what we are trying to do is that we try to make the generator to fool the discriminator as well as possible. So we are giving feedback to the generator based on how well the discriminator is able to distinguish the generated pictures from the real ones. That's like the main point in the whole system. In practice, this can be done by simply backpropagating the gradients through the whole model all the way from the discriminator loss to the generator, but we keep the discriminator weights fixed, so we are only updating the generator part and not the discriminator. But that goes into the technical details, so let's not worry about that. We keep repeating this same training step until we reach some sort of equilibrium. So we are hoping that these two models find some sort of harmony, that the discriminator keeps improving at detecting these generated, like distinguishing the generated pictures from the real ones, and at the same time the generator is getting feedback from the discriminator at how it should be producing the picture better next time so that they look more realistic. And at some point they will reach a state where neither of the models is no longer improving, and that's usually when we should stop the training. So this is how it works. Yeah.
Just to make sure I understand this, so the generator model, just in the beginning, it just creates all kinds of pictures.
Yeah. So at the beginning, we like in any neural network training, we usually randomly initialize the models. So it can be producing like complete noise. So basically, it's producing noise at the beginning if we are not in like pre-training the model in any reasonable way. So at the beginning, the generator is really bad at producing anything, and then it starts slowly getting better and better when it's receiving the feedback from the discriminator that okay, you should be actually changing these pictures slightly into some direction so that they look more like dogs, for instance.
So the discriminator gives a probability value back to the generator.
Well, in practice, it's just gradients flowing through the whole models. That's how it works. So the discriminator has basically a loss that we are trying to minimize, which is like usually a normal classification, like cross entropy. So what we then try to do is that we say to the generator that your generated pictures should look real in the mind of the discriminator. And then we can calculate the gradients, that how the generator should adapt itself so that the pictures look real like to the discriminator. That's how it works if you want to go to the technicalities.
Oh yeah, well, I can't understand the technicalities, but I just want to.
Okay, but do you now get the general idea? Basically, the discriminator is giving feedback to the generator that how the generated thing should look like, so that the discriminator thinks that they are real.
Yeah, so first it just produces noise, and then some of the noise looks a bit more like a dog.
Yeah.
The discriminator,
Yeah.
and it tells
And then
back.
and then we keep repeating this over and over again, and the generator is slowly making more and more realistic looking samples. So it's basically like you would have a student and a teacher is giving a task that you should do something, and every time you do it wrong, you get some sort of penalty, and then you get some sort of instructions that how you should do it better next time, but at no point you are told that what exactly you should be doing. Maybe this is like a bad analogy, I don't know. But the outcome is that the generator in the end starts producing things that follow the same distribution as the real samples that we have. But it has actually never seen the real samples. So in this case, the generator has never seen a picture of a dog, but through the feedback it's receiving from the discriminator, it learns that what dogs generally should look like, and it knows how to draw something like that in the end, hopefully. This is the idea. Yeah, so the discriminator knows what a real dog should look like. So the discriminator part is trained by sampling pictures of real dogs and by sampling pictures that the generator is producing. And the discriminator then tries to distinguish between these two. So the discriminator has to implicitly somehow know that what a real dog looks like, so that it can tell the difference between a generated and a real one. Yeah. So this is the whole thing. This is what everything is based on in adversarial training and in generative adversarial networks. So how does this then work in our case with the OCR project? The real data we want to use is not samples of dogs now. Instead, we have the OCR data that comes from the Finnish newspapers. And now hopefully our generator is not producing pictures of dogs anymore, but instead it should be producing snippets of text that have similar noise as what the OCR data has. So that's what the generator is trying to now produce. But in our case, we wanted to have, was there a question?
Just the visualization is confusing. So weren't the real and fake supposed to look like the same? Now we have pictures of
pictures,
sure.
So text. So these are actually would be the OCR text that comes from the scanned newspapers. They are not pictures at this point
so
anymore.
We're not generating pictures, just text.
Yeah, so just text, not pictures anymore at this point. Yeah, that's a good point. Yeah, but in our case, we actually needed to have the clean text and the corresponding text with the noise to train the denoising sequence-to-sequence model that fixes the text. So what we can do is that instead of just feeding random vectors as the seeds, we can input some sort of text as the seed. And now we then hope that the generator, when it's producing the text that should look like the noisy OCR text, it's still preserving some of the underlying characteristics of the seed. So we then end up having the same text in a clean format and in a noisy format. And now we then have the paired parallel data that we need for training the denoising model. This is the general idea. Of course, there are no guarantees that the generator would actually preserve the seed text, but that's what we are hoping for. So this is pretty much how you would do it with text. Are there any questions at this point? Is it roughly clear that how these models work? What's the basic idea behind the adversarial training?
So is your idea that the fake generated text matches the OCR with some mistakes?
Yeah.
And then you can go back to the seed, which is the proper answer?
Yeah. Okay. So now we have the clean text, and we know what is the noisy version of the same text. And now we then have like parallel training data like in any normal machine translation task you would usually use.
Yeah. You need the clean data, right?
We need the clean data, and that's but it doesn't have to be the same that we get from the news data which is noisy. So there is no correspondence between the clean data and the noisy data. Instead, we hope that the generator is able to produce noisy data that looks like the real noisy data.
Okay, so it's just a suggestion.
It's a suggestion. Yeah, it's basically a suggestion that this is what the noisy version of the clean text should look like if the OCR system had actually scanned the text. That's the idea.
So this is kind of simulating if you just took the original printer, so you would know the seed text, then you would print it out with the pad printer, and then you would use the OCR to create it in.
Yeah,
it's basically simulating the same process.
Yeah, basically, if you want to think it that way. Yeah. So yeah, basically you could do it that way. Yep. So that's pretty much what we are doing, and this is pretty much like how you would do text with these things. There is nothing. There is no difference in producing text or pictures with this machinery, except that of course the generator and discriminator will look different when you go to the technicalities. So when we are producing text, usually the generator is actually a recurrent neural network, and the discriminator is a convolutional neural network. This is like the most common setup used. But I mean, no one is forcing you to use the same setup. This just happens to be the standard way of doing things. Okay, let's get to the issues then. If it's now clear that how these things work, like on rough level. The first thing is that these things should converge to the equilibrium state where both of the models are happy. And this is usually how these models are advertised, that there is some sort of like friendly rivalry going between the models, and at the end of the day everyone is a winner and everyone can go home happily. So that's how these are advertised, but in reality it's more like Mortal Kombat. So these models are really efficient at completely destroying each other. Usually what we get is that the discriminator gets 100% accuracy and the generator is just not able to keep up, so it's not converging to anything, or the other way around. But we can also have situations where neither of the models are converging to anything, so they are just oscillating and it's completely unstable system. So this is really common. Another common problem is something called mode collapse. So what this means in practice is that we lose all the variance and diversity in the generated examples that we are producing. So no matter what the seed is, our generator will end up producing always the same example. And this is of course not what we want, since we would like to have as diverse generated examples as possible. The intuition that why this happens is basically that the generator's only objective is to fool the discriminator. So it's trying to produce examples that look real to the discriminator. And once it finds one example that looks real according to the discriminator, it can happily always produce that same example every time. And we don't really have any control over it. Yep.
So what's the loss on the discriminator? Can't it just stop detecting this real sample?
Yeah, sure. Yeah, so in practice, I mean the loss will be like your normal cross entropy, for instance, in the discriminator. So yeah, of course, if your generator is only producing one example, if it goes to this extreme situation, your discriminator should be able to distinguish it unless it's really bad one. So that's like going to the extremes that we are producing only one output. But in practice, it's not usually that severe, but we are still losing a lot of the variance in the output. Yeah, so evaluation. Note that we are still inside the issues section of this presentation. So evaluation is problematic. The first thing is that looking at the losses or the accuracies of the discriminator and generator don't really mean anything, because we can have the discriminator can have 100% accuracy if the discriminator is really good or if the generator is really bad. So we can't really make any interpretations based directly on the losses or the accuracies that we can see from these individual models. This is one paper from Google Brain, where they published like 3 weeks ago or so, where they suggest that we should actually take a bunch of generators and bunch of discriminators and organize a tournament where these things battle against each other, which kinda, I think, in my opinion, makes the Mortal Kombat analogy even better, because yeah, that's what these guys are actually suggesting. Well, of course, the research community was kind of skeptical about this. So new evaluation metrics are great, but please also measure the metrics we already understand, blah, 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 blah. And of course, it's good to be skeptical, but it didn't take long before the comments became non-constructive. So gangsters invent all sorts of excuses not to measure likelihoods. And then we went completely off topic. So I'm really sick of how hostile the machine learning research community has become, but I didn't expect you to be part of the problem. And these are top-tier scientists in this field. So if this is the civil conversation that the pro researchers are able to have about evaluating these generative models, I don't know. I guess we can just conclude that it's complicated. In our case, we are slightly luckier because we have the actual downstream task. So we are using the generative model to produce synthetic training data for the sequence-to-sequence denoising model. So we can always use the generator to generate data, train the second model with that data, and then evaluate it against the gold standard data, for instance, that we happen to have in our case. The practical problem is that it takes roughly a week on a single GPU to train the denoising model. So it's not really fun when your evaluate.py script takes a week to run before you can see the numbers that how good your model is. So we would actually like to do things jointly, so not always train the denoising model from scratch, but keep training it at the same time that we are training the generative model. This actually leads us into bigger and more complex versions of GANs. I don't have the time to go through these in detail, but there are actually dozens and dozens of variations of this basic GAN adversarial training setup. Do you have a question, or?
Yeah, maybe a little bit later.
Okay. Yeah. Okay. I'll keep talking. Yeah. The one that is particularly fitting to our case is something called cycle GAN, and this model actually has 2 generators and 2 discriminators, which are all trained at the same time. So it has one generator that in our case will learn to transfer or transform the clean text into the noisy OCR text. And then we have another generator trained at the same time, which then converts this back the noisy data into the clean data. So that's the idea, at least in theory. So we would actually get the denoising sequence-to-sequence model trained at the same time that we are training the noising model. So that's why we are now looking into these cycle GAN models, but we don't actually have any real evidence yet that they would ever work the way we want them to work. So to summarize the current state of the GAN research, there are plenty of ongoing research. I think the original GAN paper that was published in 2014 now has over 4,000 citations. So it has grown a lot, this field. These models are sensitive to everything. So anytime you tweak some hyperparameter or your model architecture, you end up not converging anymore. That's pretty much my experience. The papers or the thing published working GANs are usually full of hacks. So of course they're not calling them hacks, they call them like teaching something process or whatever, but in practice they are just full of hacks and different pre-training and all sorts of things to make these models to converge. Most of the research is still on the toy level. So we are just trying to figure out that why these models work and do they actually work. And for those reasons, the data sets and applications are really simplified, like overly simplistic. But the real applications are starting to pop up slowly. So there has been, this year for instance, there was one paper where they are producing dental crowns with these generative models. So apparently it's really complex to manually design a dental crown that looks like a real tooth and also fits the mouth of the given person. So it's better to use a generative neural network to design what the teeth should look like. So, so there are real applications coming. Yeah. So what's the state in language technology? Well, it's kind of sad. Most of the papers are focusing on unsupervised machine translation, and there it actually seems to work decently. So for like low resource languages where we don't have the manually corrected or like curated parallel corpus for training, we are actually getting decent results by doing it completely unsupervised using these methods. Yeah, but the number of publications is still really small. So for instance, if we only look at papers with the acronym GAN in the title, in last year's NIPS, which is like a general neural network conference, there were 16 papers accepted mentioning GAN, but then ACL and EMLB this year, which are like the major language technology conferences, each had only one paper that mentioned this thing. Of course, there were a handful of papers that mention like adversarial training or something else, which in practice means the same thing, but still the research field seems to be quite small in language technology. One possible reason for this is that in language we are usually producing sequences of discrete actions. So we are producing sequences of characters or sequences of words. And these models are trained like any other neural network with gradient descent. And we now would have to push gradients from the discriminator to the generator, and we have this discrete sequence of discrete words or characters in between. And well, obviously gradient descent doesn't really like discrete things, so it's really hard to make these things to converge in practice if your data is text. So in practice, many of these language-focusing models are using a thing called policy gradients, which is a reinforcement learning method, but essentially it's based on supervised learning. You have a comment? Or no? Okay, never mind. Yeah. So the funny thing here is that then under the hood we are doing supervised learning to do reinforcement learning, to do unsupervised learning, and in our case to produce training data for supervised learning. So we have this nice little circle of all the main machine learning paradigms going on in this training. Yeah. So in our case, we can produce noise. Woohoo! What an achievement! Yeah. The seed text is actually preserved under the noise, at least in our setting where we are first pre-training the generator to auto-encode the clean text. But this is like a technical detail. But yeah, so it's nice that it's actually preserving some of the seed text and not like changing the words completely to something else, which it could in theory do as well, because we have no control. But we still have a long way to go. This is not even close to the level that where we get with gold standard data, and actually not even on the level that where we get with the text repetitions and the noise we can model from those. So still an ongoing project. Yep, that's all I have for now. Are there any questions at this point?
Thank you, Kai. Yes, let's take some questions.
I have one.
Yep, sure.
Given that you have trained this GAN to produce, like you have perfectly trained GAN to produce images of dogs, how would you produce like a specific type of dog? Is that even possible?
Well, I mean, if you can, I mean, if you know what that type of dog is, then you could just filter the samples you get from the real distribution. If you have the possibility to only then have pictures of a certain type of dogs, that's like if you want to train the model to only do one type of dogs.
No.
The other thing is that you have the sampled seeds, like the random noise that you are pushing in. So usually you can start doing some sort of interpolation between the points that you have been sampling. So it's possible that if you are going to the correct direction in that space, you end up in a region where the model is only producing specific type of dogs. So you can try to find the region in that space that only produces certain type of dogs. Of course, you don't know that to which direction you should be moving. So maybe you first sample things from the whole space, and then you check that, okay, in this spot we are kind of producing the type of dogs we want, and then you sample from that region again to get like better approximation.
Maybe a little more technical example would maybe be if you're trying to make something like a product review bot.
Yeah.
How do you make sure that the review is actually relevant to the
given product?
Well,
in practice, the best way would be to somehow condition both the generator and the discriminator to the type of product that you are currently looking at. But that again means that in the real data that you have for the discriminator, you have to know that what is the type of product. So that's what you would have to then do. So in this example that I took from the one of the papers, if I can go that far back. In this case, they actually feed in one example sentence as an input, and then the generator is supposed to continue that given review. So like in this case, I mean the input sentence is not shown here, but they do have something that mentions like hot sauces, and that's why the generator knows that now it has to produce text about hot sauces and not something else. So kind of in a similar way, you would have to give the information that what is now the target that we are talking about. Well, that's one way to solve the problem. Yep.
I'm sorry, I'm just keeping on talking here.
Yeah, that's fine.
It's kind of, it turns from a binary prediction problem to kind of this multi-class. So the discriminator is not just saying yes or no, it's saying yes or no to each respective class that we are
sure. So
interested in.
if your data has this type of labels, then I think usually you should always incorporate that into your discriminator, because it will produce a better discriminator for you. So even if you are not actually interested in those labels in the end, you should still add them as targets for the discriminator.
So you're denoising the OCR results.
Yep.
Is there any reason why you're not like trying to build an OCR, going straight from
like the whole
images
OCR
to the clean text?
Well, we've been planning about that, but it goes more into the computer vision direction, and well, it would be fun to try, but there are so many of these existing OCR systems, and they seem to be kind of fancy and complex pipelines already, that I wouldn't really want to start re-implementing the whole thing again. Like if you check, for instance, the Tesseract open source one, it's kind of complex system already.
Do you think there would be any benefit of like having the OCR result that you now have, and then the image on top of that, so that it could learn at least something?
Yeah, I'm sure that if you add the picture information there, you will get better results. I don't see why you wouldn't, because that's like so obvious extra information you can add into the model. Anything else?
What type of loss functions would you use with text cams?
So most of the existing papers are using like simple cross entropy, so they are just doing like binary classification with the discriminator. But there are some recent papers that are actually doing like a language modeling discriminator instead, and then they are trying to optimize the perplexity or like cross entropy of the language model, and not just like a binary classification.
And have you used any tricks or hacks to prevent the discriminator overcoming the generator?
Yeah, we've tried plenty, usually with really bad results. But yeah, I don't know like what in the end would be the best way to do, because there are so many of them. Every paper lists like 10, and you don't know which of those 10 actually made the system to work, and you don't really want to try all of them. Yeah.
Just to get a sort of idea, like for example, like how much sort of computing power or time do you need, or would you need? Like, was the dog example you gave? Is it a real example?
No, that was not a real example.
Okay.
But something similar exists, yeah.
Okay, but how long of a time does it need per moment?
Well, in our case, we on a single like consumer grade GPU, we keep training the model 1 to 2 days usually, and then it starts producing something that at least by eyeballing looks like the noise that the OCR system is doing. But I think that depends on so many different things, like the complexity of the models you are using and so on. So if you start stacking LSTMs on top of each other, it will probably take forever to get the generator to learn anything useful. Yeah, probably it never will learn anything useful. It just won't converge at all.
What was the form of input you used to the generator?
In our case, it's just text. So, do you want like technical description of how text is usually fed into neural networks, or?
This is a kind of document that is not in electronic form, right?
So they are in electronic form.
Is it in picture form?
So we take the data when it's already at the state that someone has converted it into text format, but there can be errors in the text. So, but it is already in text format at the point that we take the data.
How large is the training data set?
For which part?
For the generator.
For the generator, we are using some hundreds of thousands of sentences.
So not large.
But you can go, I mean, way higher.
Yeah.
There are way more available, but the training times then also will start increasing a lot.
You would need more GPUs.
Yeah, yeah.
Any more questions?
How about where it works when you make this network that you use is what you input in GAN as the labels for the real network?
Sorry, I'm not following.
Et kuinka hyvin se sitten toimii, kun on otettu nämä, on master saying in English, okay.
No, you can speak in Finnish. I can translate it.
Eli tuossa käytetään sitten tavallaan, että se mikä oli tässä niin kuin se GANin inputtina, niin se on niin kuin sitten se labels.
Joo, periaatteessa niinku
niin, että saa
kohde, mihin me halutaan.
Joo, se, mihin sä haluat. Niin kuinka hyviä todennäköisyyksiä siinä tulee siinä sitten sillä lopullisella.
Yeah,
Sitten
so
kun sitä ruvetaan käyttää siihen oikeaan.
Yeah, so the question was that how well, when we are creating this synthetic data with the generative model, how well do we then do in the downstream task of actually fixing the OCR? So I think now the best attempts I've had have been something like fixing 10% of the errors on word level. With the gold standard data, we were getting to 40%. So it's like one quarter of where you can go with gold standard data. So it's not that high, but it's still something.
Any other questions?